binary system, so obviously it has two digits, 0 and 1. Now, a while ago, Diba was asking whether this was a part of architecture, and I said that for any computer science course, uh, the number system is very important. I tell you why. Because, as you will see that, or as you already know, you've done your BCA or BSc Computer Science, whatever you have done, you already know that the computer's components are made out of transistors, right? Now you see, transistors, they operate. These transistors are made out of small silicon chips, the very small silicon chips, really small. You can't see them. They're a micrometer level. You see, a 1 millimeter is so small, and a micrometer is a thousandth of that. So if you divide a millimeter by thousand and you take one part, that is a micrometer. So it's so small, micrometer level, and maybe today's hardware is even smaller. So you see, you cannot really hope to see that except underneath an electron microscope or something, which is obviously possible. Now the thing is, these small transistors, they have two reliable operating states, a zero state and a one state. What is the zero state? This is when a transistor is conducting electricity but below a threshold current or threshold voltage. One is the stage where the transistor is conducting electricity but above or at the threshold voltage, which is higher than the zero. So it may not be 0 volts and something. So people sometimes say it's 0 and 5. It may not be, it may be minus 5 and 5, it may be 5 and 12, whatever. So whatever the threshold is, but it's a small threshold, very small voltage, between 0 to 12 normally, or between minus 5 to 12 normally. So the lower threshold is always a 0, the higher threshold is always a 1. This is the operating level of a transistor. Now, when we are representing something on the computer, we will be using the transistor. So when we are representing a digit on the computer, we will be using the transistor. And a transistor can only have two understandable states, that is a zero state and a one state, whatever that means in that particular machine, whatever voltage level that means, that is. So similarly, so simply speaking, we can only represent 0 and 1 effectively using today's transistors. Okay, the components that are generally used, in fact the phone that I'm using also has this kind of a thing. So generally speaking, we can represent 0 and 1 effectively on transistor. If you have anything in between, like for example, if you had the hexadecimal number system, 16 values, 16 values, 0 to 15, 16 values, it is not possible to do that effectively using a transistor, because as I said, the operating levels, the two reliable operating levels are the below threshold and the above threshold levels. Below threshold, above threshold, below threshold, above threshold. Threshold is basically the cutoff voltage. So lower than cutoff voltage, above the cutoff voltage. These are the only two stable states. How can you in that case derive 15 different values? Answer is no, you cannot. That is why we have to switch to binary system. This is the importance of the binary system when you're studying computers, any field of computers, definitely architecture. Now let's look at the binary system now. 0 and 1. You can imagine if there are four places allowed to you, each of them can be either a 0 or a 1. These are labeled as 0 to 3, 0, 1, 2, 3. So each of these digits, they're called bits. Binary digits are called bits in short. The 4 bits, each can either be 0 or 1. Okay. And these 4 bits are taken together as one nibble, Nibble, nibble. Two nibbles is called a byte, 8 bits. Each of them can have a 0 or a 1, 0 or a 1, 0 or a 1, 0 or a 1, 0 1. In computer science, so these are 0, 1, 2, 3, 4, 5, 6, 7. Place 0, place 1, place 2, place 3, place 4, place 5, place 6, place 7. In computer science, we label this as data 0 to data 7. Why is it going this way then? Because you see, most significant digits are this side, least significant digits are this side, isn't it? If you write, say, this number 1024, this is a decimal number. So this is actually 1000 plus 24. 24 is the least significant number, 1000 is the most significant number. So this is the least significant digit, this is the most significant digit. What is the concept of least significance and most significance? It is partaking of error. If you do an error here, the error percentage will be lesser. If you do an error there, the percentage will be higher. If you just add 1 to this, this becomes 1025. Difference is 1. If you add 1 here, it becomes 2024. Difference is 1000. So this is the most significant side. This is the least significant side. So this is what it is. Least significant side, most significant side. So that is why this is labeled as D0 to D7. And it makes sense, you see, because this is units place, tens place, hundreds place, thousands place. So just like that, you have D0, D1, D2, D3, D4, D5, D6, D7. This is the convention. In some cases, the books may differ, but this is the general convention. Now, whereas one bit is written as one small b, one byte is written with a capital B. So the difference between one capital B and one small b is that one small b is just a bit and one capital B is a byte. It takes 8 bits together, 8 bits together, not separately, 8 bits together form a byte. Now, arrangements are typically in multiples of bytes. It used to be in nibbles before, say, the 1950s or 60s, but now it used to be, or maybe until the 1970s. I can't quite remember. But after that, it has always been in multiples of bytes. Like what? So 1024 bytes becomes 1 kilobyte, and 1024 kilobyte becomes 1 megabyte, and 1024 megabyte 1 gigabyte, 1024 gigabyte becomes 1 terabyte, and there are others as well which we are not going to go into. That's enough. So this is how it goes on. We go on multiplying it with 1024. Roughly this is called 10 to the power of 3, multiple of 10 to the power of 3. Actually it's more than that. It's more than that. What we roughly refer to is a kilo. What is kilo? Kilo is nothing but 10 to the power of 3. So we say it's kilobyte, ignoring the 24. But actually there is a 24 there. So like that. Okay. So always remember that although we say that 10 to the power of 6, that is 10 to the power of 3 kilobytes or 10 to the power of 6 bytes is 1 megabyte, it is actually more than 10 to the power of 6. Actually 1024 times 1024, 1024 multiplied by 1024 bytes give us 1 megabyte. So always remember that. Next one up again, 1024 megabytes multiplied by 1024 megabytes gives us 1 gigabyte, like that. It's even more. So this you've got to remember. Now,